Now for everybody's favorite, chemistry. Yeah, I'm sarcastic. Okay. Don't worry though. Actually, we are going to cover chemistry as if you know nothing more than a basic understanding of the English language, as I told you in the introduction. The ancient Greeks are given the most credit for modern chemistry, which is quite amazing. They theorized about a lot of things that came out to be true. Now, you got to keep in mind, this is when they didn't have the modern technology we have today. They had basic tests, basic chemical test, a test for hardness, and also a scratch test on a tile to look for color and streak. They were the first ones really to determine that there were more elements in the earth than just earth, wind, and fire. There are other great musical groups also. That's a joke, okay? And even though you might be listening to this home, I can tell when you laugh and when you're sincere, and grades are proportional to how much you laugh at my jokes, okay? Keep that in mind during the semester. There are 92 commonly found elements on this planet. Now, if you look at some of the periodic tables, you'll see like 118, like I have listed here. It's hard to keep up. 113, 119. Okay, they're adding elements to this. They have to create those. Again, those are not on this planet this time. I remember driving to school the one day and they announced that they had discovered element 113. And they make those in a cyclotron with subatomic particles and a whole bunch of energy. It took about, I think it was $3 million. And it lasted for 1/100th of a second. In that time, they studied it and they named it. Because it only lasts for 1/100th of a second, of course, it's not going to be in the next generation of microwaves. So don't expect to see it anywhere soon. They're doing this, of course, for knowledge. Now, where this normally forms, in these higher forms, are inside of exploding stars, and they last for seconds. But we can separate the elements into different groups. Bulk elements are ones in great quantities. Now, here we're talking about quantities in the human body. The big four: oxygen, carbon, hydrogen, and nitrogen. They moved the stick a few years ago, so now we also include calcium, phosphorus, potassium, sulfur, chlorine, sodium, and magnesium. Trace elements are ones in lesser quantities in the body: cobalt, copper, fluorine, iodine, iron, manganese, and zinc. And ultra-trace elements are ones that are very rare in the body. And you'd be surprised at what we have here. I love this example: arsenic. Of course, we think of the poison. Any of these things can poison the body, as long as it reaches toxic levels. Remember homeostasis. Okay. Too little, you get malnutrition. Too much, you get toxicity, and you poison the body. Arsenic, you don't have to worry about taking supplements. You get enough in your natural foods, believe it or not, in fruits and vegetables, that you provide what you need. Now, the ancient Greeks also theorized that these different elements were made up of particles, which later became known as atoms. Atoms are the smallest unit of an element. And so if they chopped up, let's say like a piece of chalk, they kept on in a finer and finer powder, they would finally separate the atoms. Now, atoms also have their different parts to them. Get it? Addams Family? Techie thought that was so cute. She refused to take it out. We start with element number 1, which is going to be hydrogen, the simplest of these. And we talk about atomic number, because first we're going to start with a proton. Proton is represented by a P. P superscript plus, or a lot of times just a plus sign like I have here, because of course it is positively charged. It does have mass, commonly referred to as weight. The difference between weight and mass is that weight varies according to gravitational pull. Mass is constant in the universe. So my mass would be the same anywhere in the universe. However, my weight, compared from Earth to the moon, I weigh about a quarter of the amount, which is why I would like to vacation on the moon. If I go to Jupiter, I weigh about 1,000 pounds. That's why I don't want to go there. I use these somewhat interchangeably at times, simply because I will probably never get to venture off of this planet, so they will remain constant for me. It's a weird way to look at it, but you'll see it's not the only thing I look at with a weird concept. So we have this sitting in the center of the atom, and early days they wanted to know how much it weighed. Now we know how many grams it weighs, but in the old days we didn't know, so they used a very simple system and said it weighs one atomic mass unit, and all was good in the world. This is what determines atomic number. So the hydrogen has atomic number of 1. Now the counterpart is the electron. The electron represented by E negative 1, or a lot of times is a negative sign, maybe with a circle around it, like I have diagrammatically here. Now these orbit around the nucleus where the proton is, somewhat like our planet orbits around the sun. And so it has a nice little orbit here. Now what keeps it in an orbit are two opposing forces. The one being the attraction, because as you know, opposites attract. The opposing force keeps the electron from spiraling down and nuzzling up next to that proton like it wants to. And the opposing force is going to be velocity. Between these two forces you get an orbit. And how fast it goes, if you think about how fast this International Space Station orbits around our planet, its elevation, its speed, it needs to go very, very fast in order to overcome the force of gravity. Of course, if it goes too slowly, it will crash and burn into the Earth. And if it goes too fast, it will fly off into space. So it has to be at just the right speed and elevation. Now, why it elevates so high and not, let's say, half the amount? If it suddenly dropped its elevation, its orbit down to half, it would actually have to go 4 times faster. And that would take a lot of energy. To orbit about 1,000 feet above the Earth, of course, it had to go extremely fast. And how fast does this electron have to go, considering how close it is to that proton? Again, extremely fast. Even with the best supercomputers, by the time we calculate where an electron is, it's now where it was. So it spans somewhere in this three-dimensional orbit, this shell. And the first one does form a nice little orbital, round, spherical shell here, as shown. We can think of all the shells like this getting bigger and bigger around here. That's not what happens. After this first one, they start to form all sorts of weird geometrical shapes. And you take chemistry, they'll teach you that. Actually, it's not that much use, but we had to remember those. But we're going to take some shortcuts in chemistry. Okay, in the basic chemistry like we're doing here, and also in biology, we take some nice little shortcuts. So, again, hopefully that'll help you out. So this is hydrogen. Second element is helium, atomic number of 2. So we have 2 protons in the nucleus. So now we have a problem. We said that like charges attract, so, no, sorry, opposites attract. And so like charges are going to repel. So these two are supposed to be right next to one another, but like 2 north magnets, these are going to want to repel. So how do you hold them together? That's when we use our third particle, the neutron. A neutron represented by n superscript 0, or just a 0, and this is supposed to be a graphical 0, because they have no charge. These are actually bundles of energy. This is basically atomic superglue. Has so much energy and is using that energy to hold these protons together so the nucleus stays together and we can build bigger and bigger atoms. Without it, biggest thing we could have is hydrogen, and there'd be nothing else in the universe. These also have mass, about the same as a proton, actually just off, but that's okay. Old school again, we said atomic mass unit of 1. Electrons, actually, I didn't mention, they have mass, but about 1/1000th of a proton. So you'd have to get over atomic number of 500 to get to a significant weight even to equal 1, and we're not there yet. And so we don't add in the electrons. So for the atomic mass or atomic weight of an atom or an element, we add the number of protons and number of neutrons, and that gives us the mass. This is actually the epitome of Einstein's theory of relativity. E equals mc squared. There's so much energy there that there's actually mass, which is pretty cool. And that's why in atomic reactions, when one of these disappears, there's tons of energy. We also have to cap this off with the atom has to have electrons, and so we have 2 electrons. Atoms are neutral, so number of electrons have to equal number of protons, and so it has a neutral charge now. And these 2 electrons stay on opposite sides and orbit around here. Third example, lithium, atomic number of 3. Don't worry, we're not doing all 118, only the 92. Just kidding, this is the last one. Lithium has atomic number of 3, so 3 protons. Now, how many neutrons should it need? If you don't know and you have to take a guess, the rule of thumb says the number of neutrons would equal the number of protons. Rules of thumb are usually only good about 5% of the time. This is actually good half the time. So the rule of thumb, this is very, very good. So we'll put in 3 neutrons, and of course again we have to have electrons to balance out the protons, and they'll go in orbit. The problem is when we have 2 in the first shell, and if we try putting a third one in, it'll be too close to one of these and they can't stand each other. Again, they repel, and so we simply go to the next shell. First shell is of course geometrically the smallest. It can only hold a maximum of 2 electrons. The next one can hold up to 8, so we'll put that first one in here. And once we get beyond 8, we'll have to go to the next shell, 8 in the next shell, and then some weird overlaps of subshells start to happen that usually we don't have to deal with in biology. So the rule is 2, 8, 8, 8, and who cares? Now the most important part of our atom is going to be the electrons. That's the part that's going to interact. That's the part that's involved in chemical reactions. And the specific ones involved in chemical reactions are called the valence electrons. Those are the outermost shell. Those are the ones that are going to be gained or lost or shared in chemical reactions. So since they are so important to chemical reactions, of course we give them a special name, valence electrons. This culminates now in the periodic table. Now the Russians are given a lot of credit for the production of the table. Sorry, first I have to get this all on one screen. There we go. As more and more elements were found, they started putting this weird kind of table, which might not make any sense at first. Hydrogen over here, helium way over here, and then we skip the lithium. Remember, what did hydrogen and helium have in common that they did not have in common with lithium? Why put these? These are organized into rows and columns for a reason. Notice hydrogen we put together with helium because we filled up that first shell. It has to do with the electrons, always with the electrons. So we fill up that first shell, and remember lithium started filling up the second shell with the extra electron. And we said that will take 8. And then the next one will take 8. And the next one we start filling up 8, and then that's when we get these weird transitional elements, minerals, and we say, who cares? That's when it gets complex. Luckily, even for the complexity, in biology usually we only use one form of those, and so it makes it easier for us still. Now the columns, notice hydrogen and lithium, or in column 1, what did they have in common? In the outermost shell, remember, they had 1 electron. Hydrogen only has 1, so that's in the first shell. Lithium had 1 in its outer shell, the second shell. Sodium will have 1 in the third shell, and so on. And so these actually will have similar physical and chemical characteristics. And same thing, all these together. Notice out here, helium with neon, argon. These were called the noble gases, better named the inert gases. They have a full outer shell, and that makes them usually not chemically react. They are quite content, and actually every other atom inspires to be like the noble gases and have a full outer shell. That's what causes chemistry or chemical reactions. The gaining and losing and sharing of electrons to fill up the outermost shell to be like a noble gas. There's a big difference between hydrogen and helium. You have 2 balloons, 1 of each, and you take a match and you put it to the hydrogen balloon, you're going to get a big blue flame and a little explosion. Actually kind of cool. You take that match to the helium balloon, it'll pop. Nothing's going to happen though, nothing chemically. The worst thing can happen is you inhale a little bit of the gas and you talk like Mickey Mouse for a couple minutes. So we spoke about atomic mass and also, of course, the periodic table. Keep in mind about those rows. The rows are what shell you're filling up, and the columns all have similar outermost shells, the valence electrons in common.